Hi again, AP Calc students. Here's a very important lesson in Chapter 5 called the Fundamental Theorem of Calculus. It has two different parts, one of which is a little bit unusual. You might not be able to see the significance of it. The other is very important, I feel, and we're just going to get right to it. So we'll affectionately abbreviate this as the FTC, Fundamental Theorem of Calculus. Here's Part 1. Depending what calculus books you look at, Part 1 and Part 2 might be interchanged. Anyway, here's Part 1. So we have a continuous function on a closed interval, and what this is saying that this particular function f, if we take the integral of that, that's going to equal this thing called big F of x, or the antiderivative. Anyway, here's the key thing. That function is going to have a derivative at every point. That's what the continuity implies here, and perhaps no breaks like corners or cups or things like that. Anyway, here's the key thing. Look at this. So if I take, here's the integral right here of that function. Notice we have t in here. But if I take the derivative of the integral, look at what I end up with. The original function. So the derivative of the integral is the original function. In a way, it's like one is kind of undoing the other, and we'll mention that in a little bit. Now, what's the big deal of that? And sometimes I sort of struggle with that because it doesn't seem, as we look at some various examples here, it will seem kind of silly when we look at some of these examples. But the key thing is that this fundamental theorem is the link between derivatives or differential I'll call it, and the integral branches of calculus. So we've studied primarily in first quarter, we spent a lot of time on differential calculus, of course, the derivative. Now we're just getting into integral. Those are the two main branches. This fundamental theorem of calculus is what links the two together. Otherwise, they could be two total separate entities. Really, up to this point, that's kind of what we've seen them as. But this fundamental theorem of calculus is definitely the link between those. So notice a couple other big conclusions here. Every continuous function has an antiderivative. It has a derivative, but it also has an antiderivative. And integration and differentiation are inverses. That's an important fact, too, as we go on. All right, let's look at some examples here, and some of these will seem kind of dorky. Now notice the key thing about all of these is we're taking the derivative with respect to x, but notice all of them have the variable t and dt. And as we'll see, finding this is basically as simple as undoing things and substituting something or other. Now remember we said that the derivative of the integral is the actual function. But, as you remember, the actual function was a function of x. So really, all we have to do to simplify these is substitute this x in place of the variable t. In a sense, that's all there is to it. As long as this lower integration bound here is a number, we're in good shape. And good news is it doesn't really matter at all what this number is. It can be kind of an angle, positive number, negative number, fraction, doesn't really matter. So all the answer is to this first one, the derivative of the integral, the sine of t dt is simply going to be the sine of x. We simply substitute that variable in place of this variable, the x in place of the t. All right, let's look at another one here, the next one. So again, we have a number here, x here, we have t's here. So all we have to do is say that my final answer here is going to be x over 3 minus x squared. Easy. And what might initially seem kind of trivial. Now here's the trickier one now, is our last example here. Reason that's a little bit trickier is because now we no longer have just an x up here, so we have an x squared. Still have our number right here as the lower bound. Well, here's how this is going to work. it's still going to be the ln of x. We're going to still substitute that in there, but we need to, if we remember our chain rule type idea, we just need to apply that to our upper bound here. So I might ask you, what's the derivative of x squared? And you would say that it is 2x. So we just tack that on the end, and there's my answer there. Typically you might write that in front, but it doesn't really matter too much. So that's the first part of that fundamental theorem of calculus. Seems kind of silly, but again, it's the way that links differential and integral calculus. Now here's part two, and the part that I would say is probably the more essential part, the one that we'll use a little bit more. So again, we have our continuous function f, closed interval. Here's our antiderivative, which we've done a little bit of algebraically. We'll do more of here. Anyway, here's how to calculate this antiderivative, or here's how to evaluate the integral. Notice this is our integral right here. Up to this point, we've evaluated this using our calculator a couple different ways. Using the calculate menu that actually draws the graph. We also saw that there is a numerical integral option on our calculators as well. But notice what this says. Here's a way to evaluate this integral by using the antiderivative. So the idea here is that now we can calculate integrals algebraically, and so we have no need of using our calculators. We'll still use our calculators to check, of course, but this is an algebraic way of evaluating integrals. So that should make you jump for joy, like this kitten. Alright, here's some examples. Let's take a look and see what they're like. Alright, first of all, you have to think about antiderivatives. And remember, antiderivatives generally have bigger powers. So what's the antiderivative of x squared? Well, it should be x to the third, but then it also has to have a 1/3 in front of it. And remember, to figure out if you have the right antiderivative or not, just take the derivative of this. 3 times 1/3 is 1, and then x squared. So yeah, sure enough, I get back to that. So that's my antiderivative, and then I evaluate it between these two values. And a lot of times I'll draw that straight line like that, or put a 3 and a 0. So then I just evaluate it like this. I put the 3 in place of x, and then I have to subtract, and then I put the 0 in place of x like this. Well, 3 to the third power, that should be 27. And 27 times 1/3, or 27 divided by 3, should be 9, I believe. Meanwhile, 0 to the third is just 0, which gives me 0 here. So the answer to this integral is 9. Now, we'll do some tougher ones than this, but this is just kind of a basic example. Alright, let's look at the next one here. Integral of cosine of x dx from pi over 2 to 3 pi over 2. Now you have to think about this for a bit. What is the antiderivative of cosine? And it's going to be sine. Remember, the integral of sine is cosine, so the antiderivative of cosine is sine. And again, we want to evaluate this between 3 pi over 2 and pi over 2, like that. So then we have to take the sine of 3 pi over 2 minus the sine of pi over 2. So again, if we think about this on your circle chart, you might remember that sine is your y values. Sine of 3 pi over 2, 3 pi over 2 is way at the bottom there at 270 degrees. So that's going to be -1 minus sine of pi over 2. Pi over 2 is kind of, it is at 90 degrees. Sine value there is 1. So -1 minus 1 is -2. And you might say, well, wait a minute, is it possible for integrals to be negative? And sure it is. Remember, that's just the area under that particular curve. Now on our next slide, we'll just double check to see if these are correct. Sure enough, I checked this on the calculator here. Here's the integral of x squared between 0 and 3. And sure enough, that's 9. Definitely a positive area here. Here's the one we just did for cosine. Keep in mind, this is the cosine graph, and this is the area we're looking for between pi over 2 and 3 pi over 2. And sure enough, it is that -2 that we found on our last slide. So this is the fundamental theorem of calculus, and we'll be working on that the next couple days. Thanks for listening. We'll see you guys in class.